you cut bread, you're shearing bread.
So when you stand on a skateboard,
When you stand on a skateboard,
the truck.
you are causing some bending, right? And if your load is big enough, if you were an elephant, you probably would shear the skateboard at the point where the elephant puts his weight on the skateboard, right? If you guys stood on a skateboard, it would just bend. It's supported on the ends by the wheels, simply supported, right? What would those be? If it's touching the ground at the wheels, we're looking at normal forces, right? It would be normal forces at the end, okay. Normal forces at the end, and then we're causing it to bend in the center. Same thing if it's a cantilever, and I'm connecting it, and I put enough load here, I'm actually causing bending, cantilever bending. But I probably can't shear a skateboard unless I put a big enough load. And there are two ways to put on the load, like put that bottle on here. You can put the bottle on here, and that's called statically loaded, because it's put on gently, even if the load was increasing. If we were pouring water in the top, it would be gradually, the weight would be gradually increasing, and that would still be called static. JJ, did you take materials of me?
No.
What's a dynamic load? What's a dynamic load? Yeah.
Jump on the
Ready?
skateboard.
Good. That's a dynamic load. It's an instantaneous load. If you were trying not to break something, would you apply a static load or a dynamic load? Static. So we know the term static is not moving, right? When we're now analyzing things, it's not moving. But when you're loading something, when you load it statically, you're putting the load on slowly, or you're gradually increasing the load, put more water in. A dynamic load, so if I took the ball and threw it against the wall, what would that be? Dynamic. Okay, so now let's relate this all. This is all material properties. So now we're relating it back to statics, what we're doing today. When we have a beam, and Gigi, could you put that on again? I'm supporting it on its ends. If the load here in the center is large enough, I could cause a shear failure, right? If this was a huge load, I could cause a shear failure right here. The shear failure wouldn't be caused here. The shear failure would be caused here. But let's say the failure was on the ends at the connection. What else is this doing besides causing this beam to fail and shear?
Reaction.
Bending. Well, torsion if it was twisted, right? Let's assume that it's centered. Sorry, I just put my head on my chin. But it could cause bending failure, right? If I have a beam that's cantilevered, and I apply a load, I might be able to shear it here. Or if I apply a load, I might actually cause it to snap due to bending. So when we're looking inside the material, the strength of the material, that's me, sorry. If we're trying to look at the strength of the material itself, we have to figure out, well, how much can it take in shear and how much can it take in bending before it snaps? You probably know most times failure occurs at connections. The reason why is because we know how strong this thing has to be. Right? We always know how strong this thing has to be. So things very rarely break, fail, due to the strength of its material. It's usually where connections are. Even though we know what the connection has to handle, sometimes you just get a different load than you expected and it tweaks the connection. So all along in statics, we've been looking at, well, most recently, we've been looking at loads that are in connections, right? So we can design a pin or a fixed support. But now what we're looking at is we're looking at the internal, what this material is experiencing inside. What kind of shear loading does it need to experience? What loading does it need to be able to resist in terms of shear and also in bending? So we're doing my favorite topic, shear and bending moment diagrams. It's all diagrams. Isn't that cool? Okay, I'll show you how to do the math at the end, but for now, we're just gonna do it all the diagrams. So I drew everything up for you already. So take out those two sheets, we're gonna work with one at a time. And there are two of them, so you have to, no, they're on the file, on that desk. Oh, they get it. You get two sheets. Wait, let's take two from Valerie. Wes. Vivian. Okay, so it's all drawn for you already, okay? So everybody look up here. So we have a beam. You can put a light on if you want. We have a beam and it's connected somewhere. It's got to be connected in two different spots, right? Because typically we're not dealing with cantilevers. So it's connected in two different spots. So the first part of the problem is you look at all the loading that's on the beam and you have to figure out the reactions of the supports, which you know how to do already. How would you, if they're both normals, even if there are two normals, or there's if there are two rollers, you have two normals, right? How would you figure out, what equation would you choose to find one of them? Some of the moments about one of the points will give you the other force, and then what equation would you do? Some of the forces in the y, and you find them. And if you want to do a check, what would you do? Some of the moments about the other point. So we already know how to do that, so I've already found them. This right here is a reaction at support. This is a reaction at a support. Reaction at support, reaction at support. So I already calculated that because I don't want to waste our time doing that. You already know how to do that. I want to do the shear and bending moment diagram. And this is how it's abbreviated. V is the abbreviation for shear. And then of course bending moment, BM, bending moment. So we're doing shear and bending moment diagrams.